My name is Devikrishnasai. I recently graduated from LHPU in mechanical engineering. Most of my work involves controls, ADAS, systems engineering, and some of mechanical design. So today we are here to do a presentation on the topic that we did as a 6-week course at LHPU. Fundamentals of Automotive Functional Safety Systems using ISO 26262. So let's get an overview of the whole topic. So our main goal is to control a Cummins diesel engine to limit its maximum speed and to keep it at a certain idle speed. To do that, we made a PI controller using a min-max governor model in Simulink. We implemented CAN communication using the J1939 protocol. We performed a HIL testing to eliminate any errors and to validate the model. And we also implemented functional safety and FMEA in the whole process. So this is the procedure. We have 4 different types of topics today. We have the electronic throttle control, the hardware load testing, the engine test cell, and the functional safety. Although the functional safety has been applied all through the process, we'll talk about that at the end. And then the engine throttle control. So this is the one that we find the practical application of that every day in our lives when we switch on the car and then go forward. So electronic throttle control opens up your throttle valve, allowing your mixture of fuel and air to go into the engine and make the car move forward. And then this is done by using a PI controller, and we use a Woodward ECM. It's called an engine control module, which performs certain actions in the engine. And we also implemented CAN communications. We performed a distributed control system, which we'll talk about later in the slides. And we also learned about sensors and actuator blocks. So this is the whole model of the ETC. We have a sensor block, which gives out sensor inputs such as your accelerator pedal position and your throttle position sensor, which means where your throttle is open or like how much your throttle is open. And this is being fed into the PI controller. PI controller is a controller which works on a feedback. So the feedback being the state where you are, and then your goal being the state where you want to be. So the PI controller calculates that difference and does calculations with the P and I gains with that difference and gives you the required output. In our case, it's the output to actuate our motor to open and close the throttle valve. We have a video of ETC working. As you can see, if you move the pedal position, we have the throttle valve opening and closing, which allows the air fuel mixture to go into the engine and make your car move forward. And then we did the same thing on a distributed control systems. Sometimes when in the real case scenarios, when things get really complicated, one single ECM cannot handle all the work. So we do distribute the work between several ECMs. So we did the same thing in our case. We had 2 ECMs, and then we had a CAN wire in between them, making them talk to each other to perform the same action that we saw in the previous video. And then next, we go to speed governors. Speed governors are the ones you find in your vehicle once you start the vehicle. You can also find that your engine is idling at a certain RPM in your tachometer once you start the engine. And then your engine is also limited to a certain maximum speed. Even that is done by the speed governor. So in this case, we have 2 governors, one the minimum and the maximum. The minimum takes care of the engine idling part. The maximum takes care of the limiting the engine to the maximum speed. Now, even this uses a PI controller as before, but the PI controller in this module is a little bit more sophisticated than in the ETC. And then we have the limits. So we want the engine to be idling at 700 RPM, and then the maximum speed of the engine to be 1700 RPM. And then the working, this minimum and maximum governor gets activated once you start the engine, and then they provide certain fuel and then remove certain fuel from the engine to achieve the desired stage. So this is the whole model of our minimum and maximum governor. So we do have an engine manager which says which state your engine is on. We have 3 different states of engines: stall, crank, and run. The stall state says that your engine is switched off. The crank state your engine is switching on, and the run state says your engine is switched on. So in these cases, for the crank state, you provide 0 fuel because your engine is switched off, and the crank state fuel depends upon engine and application and how your engine responds to a certain input. And then the run state is the one where we place our both minimum and maximum governors once the engine starts running. So this is the insights of the stall and the crank state. As we talked about before, we have 0 fuel for the stall state and then a certain fuel for the crank state, which can be modified. And then we'll go to the run state. The run state is the one where we have the governors, and then the run state has several different subsystems. Let's go through each one of them, and then we'll see the models in the slides. We have a state manager. It's almost same as engine manager, but it says which governor should the engine should activate in order to maintain the desired speed. And then we have set point. Set point is our target that we have to reach. In case of a minimum governor, the set point will be 700. In case of maximum governor, the set point will be 1700. And also we have PI controller in this one for the maximum and minimum governor separately. And then we have an initial condition. This is specific to max curve. We'll see about that when we reach max curve. And then this is the whole run state. You have the min curve controller, you have the max curve controller, and the final output is the fuel that is sent to the engine. This is the minimum governor. We have a state manager which says your engine has just started, so enter min curve and then maintain the engine at a certain idle speed. And then the set point is the one where we set at what speed our engine should be idling at. So in our case, it's 700. And then the min of PI takes a difference between what the engine is at and where it should be, and then calculates that difference to give out the actual fuel that is required by the engine. If it is at min of state, it gives out zero fuel. It gives out zero additional fuel, so that it remains at the same stage. And then we have the maximum governor. This is where things get a little bit sophisticated and a bit more interesting. We have another block called the initial condition manager. This block is placed because the max curve works in a way that it removes fuel from your pedal when it thinks that you're providing too much fuel and the engine is exceeding the maximum speed limit. We have a state manager, initial condition, set point, and the max curve PI. And this is the state manager limits. So state manager gets activated when your engine is at 1500 RPM, but it stays on hold until the pedal you press is more than what max curve thinks the engine should require. And then we have the initial condition. This is measured based upon how much faster your car is accelerating. If your car is accelerating in a faster rate, it will take more fuel from the engine. If it's doing at a slower rate, it will take less fuel from the engine. That can be done by the APP FPC offset graph here, which correlates at what acceleration, how much fuel should the engine be taken out. And then we have the set point manager. This is where we set our set point. In this case, it's 1700 as a maximum speed that an engine can reach. So we have set point at 1700, but we do have a APP FPC offset again, so that it gives an accurate value and it won't have any overshoots when it's reaching that maximum speed state. And then we have the PI controller. In this case, we have two main things to talk about. One is the hold state here, and one is the reset state with a dynamic input for the item. So as we talked about before, when the engine reaches the maximum governor state, which is above 1500, your P-term goes to hold and it doesn't provide any fuel when your accelerator pedal is less than what the min of fuel is. And then if your accelerator pedal is more than what min of thinks it is, it will start activating both the P and I terms, and it will start removing fuel from the engine to maintain that 1700 RPM of the maximum speed. And then this is the most interesting part. We faced a couple of errors up to this point. One is a canvas error, which is occurred in the ETC, where we accidentally put the canvas as none. So it didn't have any port for the ECM to communicate with. So we had no messages coming into the canvas through the ECM. So then we traced back the error, and then we had to do a soft boot to again reprogram the ECM. And set point error, this is an error where it occurred in the engine test cell, but it's due to the max curve controller. We had set point of very high numbers in the order of like 1.3 e⁻⁷, that is around 30 million RPM. So if it's the practical case, your engine will probably blow up with that set point. As you can see here, there's a green line indicating the 13 million set point. And then we trace back what is causing this error. So this is caused by set point. So we had three inputs for the set point. One is the speed, one is the state, and one is the acceleration. The speed is given by the sensor, and the state is active since we could see it working because the max curve is getting activated. And then there's another input called acceleration. So we trace back that acceleration to the initial condition manager, and then we found this. In this one, we put display blocks after your data pass every subsystem to see how it is changing. That didn't give us any results because in the accelerations subsystem, we removed this data type conversion loop blocks, which has been creating all the errors. So we then figured out how that unsigned in16 data type conversion block works. So normally that has a range of 0 to 65,535. We assume that if it would get a negative value, it would round up to 0, but it worked like a Python array. When you give a -1 as an index in an array, it goes to the last value in there. So we're not sure. We then concluded that that was the process going on in the embedded C code when we convert our simulating model into the ECM. So when we had an input of 20 for the conversion block, it was working fine. Since it's a time step of 5 milliseconds, we got a value of 4,000, which is perfectly fine in this case. And then we had an input of -1. This time we got a value of 65,535. And then divided by a time step of 5 milliseconds, you get 13 million, which was been crossing all the problems. So this is the end of my presentation. The next topics, HIL testing and the engine test and functional safety, will be covered by my teammate Srinath.
Hello, my name is Srinath. I completed my master's in mechanical engineering from the University of Texas at Arlington. I particularly took this course to kickstart my career in controls and systems engineering while applying my mechanical engineering background to the electrical systems and real world. So today, I would like to present about hardware in the loop HIL testing and engine. Talk about the engine test cell, what we did there, and a basic overview of the functional safety. So in hardware in the loop testing, it proved as an effective solution to test the control systems. The HIL simulation gave us the satisfaction of verifying and validating the simulated engine model and giving us the confidence to run a live engine with our design model. Simulated testing provided solutions to detect several issues with the controller, sensors, and actuators. That would otherwise damage a real engine plant or would be harmful to people in real situations. This greatly enhanced the safe operations of the diesel engine. I found like 5 benefits of HIL testing. It mainly increased the safety of the engine plant. It enhanced the quality of the engine, saved money, saved time, and also increased human safety. So my basic understanding in the hardware in the loop testing, after the simulating design, we flashed the model onto the Motor ECM 4805, used 3 dual PSP blocks as fuel injector output resources for the VP44 to build a sync pulse signal, used CAN-KIN to transmit CAN messages from the VP44 as per the CAN requirements to the Motor ECM, calibrated the PI gains of the min and max governor, feed forward fuel to the engine in order to make the engine run to the min governor or max governor, and also calibrated APP gain and offset to produce the desired output for the engine. Most of our HIL testing was based on the actuators block here. We sent like 5 messages as per the CAN requirements that were needed. Here H-bridge is used as a lift pump which provides fuel to the engine. H-bridge is an electronic circuit that reverses the polarity of voltage applied across the load. It is most commonly used in automotive applications to generally run the motors backward or forward. This lift pump provides fuel to the VP44. VP44 is the fuel injector pump that is used in the diesel engine, which takes the fuel and controls the fueling amount based on varying engine speeds. Start of ignition was given as 28, and the start of pumping, which is the CAN time, is set as 0. We send these CAN messages to the ECM connected to the live engine that makes the engine run. This is our simulated engine model. At first, when we ran the HIL model, all of our engine lights were on. The first 5 lights were there because of we sent the wrong CAN messages. The engine uses a 29-bit extended CAN identifier, but we gave this message format as standard, which should have been extended. This resolved this problem. For the lift pump, we changed the step change. We gave a step change of 2 to 2.2 seconds. Basically, it is giving time for the lift pump to settle down as it gives fuel to the engine. 2 was very much little time, so we gave it 2.22 to solve this problem. This is the experience I gained from the HIL testing. I got hands-on experience on simulating design, motor code generation, motor tune calibration, and CAN. Moving on to engine test cell, these are the 3 main topics I want to cover in the engine test cell: pulse synchronization, motor tune calibrations, and running the live diesel engine. In pulse synchronization, sync pulse signal from the VP44 fuel injector of our model is compared with the Cummins reference signal using an oscilloscope. The 2 important parameters were TDC encoder offset, which is the crank sensor, crank sensor of the offset, and the injector offset duration, which is the offset of the VP44 injector pump, which helped in matching height and width of both the pulses. Though the engine firing order is 153624, it is handled by VP44's external plumbing. Hence, we fire the pump in an order of 1, 2, 3, 4, 5, 6. This is where I gain an excellent understanding of motor tune while running the live engine. I got to modify various parameters of the engine controllers, sensors, and actuators to run the live diesel engine as per the requirements. Chart comparisons were made between the RPM and the minimum and maximum governor to run the engine with the desired requirements. The requirements we have to meet were keeping the engine at an idle speed of 700 RPM, that was the min-gov calibrations, avoiding accelerations at full throttle beyond 1700 RPM, where we did the maximum governor calibrations, and avoiding overshooting of RPM while the engine is in idle state and in run state. That's basically calibrating the proportional and integral gain of the control. So these are the important motor tune calibrations we made while running the engine. Encoder TDC offset and the injector offset duration. This is offset duration, sorry for the mistake, I gave the wrong name. These 2 were the important parameters to synchronize our pulse with the Cummins reference pulse. And we gave a crank state fuel of 70. It was different in the HIL model because in the live engine it needed much more fuel to crank the engine. And here we did one mistake here. We previously gave the values from the HIL model. When we tried to start the engine, it made a weird sound when we tried to start the engine. So what we did was we calculated the ATP gain and offset at an idle state and at full throttle in order to compare it at 0 and 100%. In order to make the engine run at minimum governor and maximum governor, feed forward fuel is an effective way to do that because the engine needs a little push to make it run. So if we could change, give a little bit of feed forward to both min and max gov, the engine would get the necessary fuel to run. So this is our output chart. So when we started the engine, it was working fine since we calibrated the P and I gains of min-gov. But when we suddenly gave the full throttle, it just reached beyond 1700 and matched with the desired RPM. But when we actually gradually give the pedal as in real life conditions, it would smoothly go and reach our maximum power. This is a video of us running the live engine. The first time it didn't start. So as we calibrated the P and I gains of the minimum governor, it is running very smoothly in the min-gov state. And as we gave a full throttle here, we also calibrated the P and I gains for max gov. So that's also running smoothly. So we gave varying pedal questions to see how the engine is working. And to my satisfaction, I would say that we did a good job on calibrating the engine controller to make the engine run well. So, I would just like to give a brief overview on the functional safety topics we covered during this course. And I felt like these were the 4 important topics that that were covered would help me in my career. ETC test cases, FMEA cases on APP and TPS, HARA and FTA. HARA. HARA is hazard analysis and risk assessment, which is an efficient process to identify the potential hazards that can cause harm to the surroundings and evaluating the risks associated with it. HARA can be determined by these parameters: severity, how severe the hazard can occur, occurrence, so the frequency in which the hazard can come, and controllability, how well we can control the hazard when it occurs. FTA. FTA is fault tree analysis. It's a graphical tool which uses logical Booleans to explore potential cases of system failures, system level failures. FTA uses a top-down approach where the top event indicates the critical system failure, and we work down to the bottom where the bottom level indicates basic component level failures. So we also performed 2 FMEA cases on open circuit for accelerated pedal position and throttle position sensor. In an open circuit, the output would be 0. So the failure mode is analyzed by creating an FMEA table. The main purpose of FMEA table is to calculate the risk priority number, which is a product of severity, occurrence, and detection. We calculated it and found out ways to how to reduce the risk priority number. The basic solution for this would be to check the wire harness and make sure that the hard wiring configurations are done right in order to avoid the open circuit. So we performed 2 ETC test cases. The first test case was power failure. Disconnected the power supply from the throttle valve by disconnecting ETC relay pin. This turned on the fault light indicator lamp, verifying the power failure. So this is a video of us doing the power failure test. So when we disconnected the ETC relay pin, the fault light indicator turned on. So that the second test was stuck throttle valve. We manually obstructed the throttle by placing some sort of obstruction. Use the accelerated pedal to command to close the 0%. That means try to close the valve by moving the throttle position, which eliminated the fault lamp. So after removing our obstruction and we tried to do the same thing, the stuck valve indicator has been removed. Thus verifying our test case. So when we planted an obstruction in the throttle valve, the fault line indicator turned on. Thank you. Thank you so much for taking the time to see this presentation. It was a great opportunity for us.